Okay, so the recording has started. So, hello and welcome everyone. So, this is our last talk for the semester, and today we have Abhishek, who just defended his PhD thesis few months back. He used to be a PhD student at IIT Delhi, and he will be talking about his work that appeared at Uppsala last year, right? So, Abhishek, over to you.
Thank you. Hi, my name is Abhishek, and I'll be presenting a work titled Modeling Dynamic Deallocations and Allocations of Local Memory for Translation Validation, which is a joint work with my guide professor Saurabh Bansal from IIT Delhi. This work was accepted in UPSA 2024 last year. So my work is about translation validation. Brief background. So a compiler takes a C source code and
Abhishek,
translates it. Hello?
Abhishek, yeah, sorry to
Yes.
disturb. It seems the audio is bit thin. It's a bit glitchy also. Uh,
I see.
maybe if you can speak a bit louder, that will be fine, I guess.
Okay, I'll try speaking loudly. Okay,
Yeah, yeah. Please go ahead. Yes.
yeah. So translation validation relates to the problem of compilation. A C compiler takes the input source code C and translates it, compiles it to an output assembly. A translation validator passes a judgment on this translation. So it takes the same C source code C and the generated assembly A and answers the query whether the compiled assembly A has identical observable behavior at the C as the C program C. So it's about validating the translation. So translation validation. So in my particular setting, we are dealing with what we call end-to-end translation validation. We consider the input program to be an unoptimized IR of a C program. So we don't directly deal with the C program. Rather, we consider an unoptimized IR, which can be obtained by through a syntactic translation from the C program. And for the assembly side, we consider 32-bit x86 assembly. So this is our end-to-end translation validation setting. Our translation validation will pass judgment whether the two programs are equivalent or not. And the assembly program is supposed to be generated by a C program by a compiler. So our focus is on the C program which has particular constructs which are the local memory allocation and deallocation constructs. These constructs are address taken local variables, fixed and variable length local arrays, a lookup operator, and variadic functions. We'll see examples of these constructs soon. And we define correct translation as a refinement of behaviors. So this input C program C has certain behaviors, and the assembly A has certain behaviors. A translation is considered correct if the observable behaviors of the A assembly program is a subset of the observable behaviors of the C program C. Right. So C is non-deterministic. So this subset relationship is acceptable. A brief overview. So as I said, translation validation is about verifying correct translation. So we have two programs, a C program and an assembly program, and we check whether the behavior of the assembly program is a subset of the behaviors of the C programs. So while translating from C to A, the compiler chooses a particular allowed behavior. For example, in C, the following behaviors are non-deterministic. Example number one, address an initial value of a local variable. Number two, order of evaluation of procedure call arguments. For example, if you have a procedure call printf, which has multiple arguments, the order in which the arguments are evaluated is non-deterministic in C. And the compiler is free to choose any particular order. And the third example is the order of evaluation of LHS and RHS of the assignment operator, the equal to operator. So if you have A which is assigned to E, then the order of evaluation of A and E is not specified. Right, so it's not deterministic. The compiler is free to choose, free to make any particular choice. So in the prior TV work from FM8, PLDI 19, and UPSLA 20, correct translation was formulated as identification of a simulation relation. and which is obtained through a construction of a product program which relates paths in A with set of paths in C. So if you have an assembly program, you relate a path in the assembly program with a set of paths in C, and you construct a lockstep correlation between the two, and that's how you identify a relation which can be formulated as a refinement of behaviors. So in this prior work, locals were not modeled, and other non-determinism was handled by essentially making the same choices as the compiler. So largely the compilers make the same choice for each input. For example, in case of the third example assignment operator, the compiler will make the same choice largely the same choice each time it compiles a C source code. So by fixing the particular choice for a particular compiler, it was the translation validation was possible. So in our case, we handle the third case, which is the address and initial value of a local variable, and we generalize this handling with this fixed handling to a dynamic handling where the choice can be the choice is determinized on a per program basis rather than a per compiler basis. A motivating example: consider this C function readInt. It has a local variable x whose address is taken and passed to this external function scanf. So scanf takes the address of x and then returns the value x. So this variable x is called an address taken variable. So because the ampersand operator is applied over it. So this was the C source code. In our unoptimized IR, which our system deals with, the allocation and deallocation of x is made explicit through alloc and dealloc instructions. So in the instruction I1, we can see that x is assigned through an operator called alloc, which allocates x. Then in the second instruction, we pass the obtained value to the function to the call of to scanf. Then finally calculate the return value by dereferencing the pointer of x, and at the end, just before returning, we deallocate x and then return. Right. So the allocation and deallocation, which was implicit in the C program, is made explicit in our optimized IR. Right. So allocation. So let's go over the semantics of allocation and deallocation. So the semantics are that the returned address, the alloc operator, the address which it returns, which is the address of x, it's non-deterministic. Similarly, its value is also non-deterministic, that is dereference x or star x. But they are not truly non-deterministic. There are certain well-formless constraints that are imposed by C. These constraints are that the allocated interval, that the 4 bytes of x, that is from x to x plus 3, both inclusive, it does not overlap with currently allocated regions. For example, if there was an allocation in the caller of readInt, then it must the interval returned by alloc must not overlap with it. And the second restriction is that the address of x must be aligned by the required alignment for the type. For example, int requires an alignment of 4, at least 4, right? So the alloc operator returns a value, a pointer, or an address or interval, uh, which satisfies these two well-formless constraints. Next we tackle the case of a procedure call. So the procedure call, in this case scanf, has two arguments, a string percentage %d and the address x. So this scanf being an external procedure, so by external procedure, I mean a procedure whose definition is not available in the current compilation context. Usually scanf is provided as a system library and which is linked later during link time, and at compilation times, the definition is not usually visible. So the definition is not visible to compiler, only its signature is known. So this scanf, uh, by virtue of the C semantics, it can observe both as it is passed the address of x, it can observe both the address and the value of X. And since the definition is not available, a definition which can be later loaded, uh, it can potentially observe it, which means it can maybe print it. For example, you can have custom definition of scanf, which is printing all the input arguments before scanning, before doing the actual scanf function. So the for our semantics, we require that the observable behavior of the two programs are equivalent, right? So because the not available, the observable behavior of scanf constitutes the observable behavior of the readin function, readin procedure. So so as we can see, scanf is observing the address and value of this constant string, which we can ignore. Uh, the interesting case is the second case where it is observing the address and value of X. Recall that the address and value are non-deterministic. So the scanf is potentially making observing a non-deterministic value, right? So this point is important. We'll come to it later. Second, so on the left is the assembly generated by a compiler for the reading function. So for locals, the compiler uses the assembly stack. So x86 has a machine has a stack whose lower value is controlled by the stack pointer ESP. So all the locals are allocated on the stack. So the variable x, which was a local, so this x is allocated on stack in the assembly. So in the first instruction, the compiler is allocating decrementing the stack pointer. Decrement in the stack pointer corresponds to an allocation of stack by 20 bytes, thereby uh, 4 bytes, at least 4 bytes for the variable x. In the next instruction, it is doing something related to the procedure call instruction, but we'll ignore that for now. And so the 4 bytes out of these 20 bytes correspond to the local x. So our problem is that because the scanf procedure is because the scanf procedure is observing the value of x, we must establish a correspondence between the stack address and the address returned by the alloc operator. So as you can see, this correspondence which we require is lost by the translation from C to assembly or the IR to assembly. And this correspondence is what we need to recover to be able to relate the two scanf calls. So this is problem number one. Another big issue is that this stack pointer decrement or stack allocation may potentially overflow the assembly stack. For example, consider this case where the 20 bytes allocation actually overflow into the program heap. So if this happens, the program is terminated by the operating system, by the environment, runtime environment. And this is one of the problems that must be dealt with while dealing with assembly. We'll come to it later. First, we'll give a brief overview of how we establish refinement. So formally, we define a trace T as a sequence of observables. So what are observables? Observables are values of variables, registers, memory contents, events such as procedure call, procedure return, halt, error, and so on. So a trace of program is a sequence of observables, and we say that a program executes with trace, say t sub p. So program p executes with t sub p. We say that it denotes a condition that procedure p, through a sequence of non-deterministic choices, may produce a trace of observables t sub p. Right. So consider this example of a written procedure such that this relation holds. So this is our program. So first observable is a call begin event. Second is the argument 1, which is hex 1000 in this case. Then the argument 2, which is hex 2000. Then the memory contents of heap, memory contents of X. So these are the observables that are part of the trace of T sub readint. Then there is call end, then a return, and then a halt. So this is a trace of T sub readint. So we say that correct translation such that A defines C, or denoted as this subset of relationship, that C is a superset of A if and only if A executes with the trace T sub A implies that either the stack overflows. So this particular W of T sub A denotes the condition that stack overflowed, or the C program exhibited UB. So a UB in C corresponds to an undefined behavior, a behavior for which no definition is provided by the C standard, and any program which exhibits UB is said to be a non-conforming program, and the compiler is free to give any behavior in this condition. So it's a sort of an invalid C program. So in such a case, if the C is exhibiting UB, the compiler is free to omit any assembly. So we say that the refinement holds in any case. So at the moment the program exhibits UB, the refinement automatically holds, right? And the third condition is that there exists a trace T sub C such that C executes with trace T sub T and both traces are identical. So we say that A is a correct translation of C if A produces a trace T sub A where either the trace ends with the stack overflow, the refinement trivially holds in that case, or the C program exhibits UB, or the traces generated by C program and the E program are identical. So notice the exist symbol in this case. So it allows that the C program to have multiple non-deterministic behaviors, and the E program is only needs to satisfy one of them. So it can choose one of them. So this is a definition of correct translation. Now let's see how it fits with the semantics of external call procedure call in assembly. So in the C program, the call to scanf has explicit arguments. So scanf has argument number one this, argument number two that. In the assembly, the call instruction has no such explicit arguments. In fact, the opcode for assembly is just the target for the instruction pointer. So it does not have any explicit arguments. Instead, the arguments are implicit. So the arguments, in case of 32-bit x86, the arguments are pushed on the stack. So in this case, as you can see, A456 is first pushing the two arguments and then calling scanf. So identifying these two arguments is a challenging problem, especially if the target callee is a periodic function like scanf. For example, it could have been three arguments here. So that's the first problem. The second problem is that the behavior of an external callee in assembly cannot be bounded over. In case of the C, the behavior is bounded by the certain semantics imposed by C. But in assembly, no such behavior, no such bounds exist. The target is allowed to have any behaviors. There are no such constraints over the behavior of callee in assembly. So what we want to express is that what the target callee in assembly can do or cannot do. So for example, one thing that we one thing that we definitely want to verify is that after the call to scanf, the call stack of readint is not modified. So this condition is required by the calling conventions so that the compiler can do, for example, do register spelling, right? So a solution to this problem is that we maintain complex invariants particular to each callee, and these invariants have to be identified and reduced correctly. So another solution that we propose is that we identify these events and call events and local allocation events distinctly, so that we can express what the assembly program is doing and correspond it to the C program. So key idea in case of allocation is that we identify the local region distinctly from the rest of the stack in assembly. So let's go back to the original assembly program. So the local X is allocated in the C program. In the assembly program, the local X resides in the 20 bytes allocated by the C program. So what we want to do is want to identify the 4 bytes corresponding to this local X in the 20 bytes of the read-in stack, right? And the way we identify them is through annotations in the assembly procedure. So these annotations correspond to uh, assembly new assembly instructions, which are just notations. They do not have any meaning in the assembly semantics, and they are only valid for the validation purposes. So annotation instruction in assembly. So first instruction that we introduce is an allocation on stack instruction, which is alloc sub s or alloc s. So the semantics of alloc s are such that it takes a address addr for adder, size se, alignment align, and a local id for identifying a particular local allocation. So the semantics are that it identifies the region starting from adder of size SZ as belonging to local ID. So the interval ADD adder to adder plus size minus 1 is essentially transferred from the stack to the local, right? So the local is identified by this local ID. So if we can track these addresses precisely, such that the out of the total address range available to stack, we can subtract these address ranges from this from the stack and assign it to the local. Then we can essentially correlate these address regions in the C program and the assembly program. So continuing, these the semantics as we had for the alloc instruction or alloc operator in the C program have well-formness conditions that correspond to well-formness in assembly. So one of the well-formness condition, as expected, is that the this address range actually does not belong to the stack region. Sorry, actually belong to the stack region, not and not to something else, so that we can actually transfer it from the stack to local. Similarly, the target adder must be aligned at least by the aligned region, which is required for the local. Right. So these are the semantics of allocas that we impose, and our assembly program will be annotated with these instructions that allow us to correlate the two programs and establish correct translation. So the second instruction that we have is the dialog as instruction, which essentially transfers the interval back from the local to the stack. So it undoes the work of the locus instruction. So one particular aspect that is required for establishing correct translation is that the annotations that we perform on the assembly program, they must be sound. So what we want to express is that the annotation must correspond to so if we annotate an assembly program with an allocus instruction, then it must correspond to an annotation to an allocation in C. So the way we enforce it is by letting the allocus and alloc instruction produce observable events. So recall that in the prior work, the by construction of a product program, the correct translation was achieved. So if you are able to correlate observable events somehow, we'll give a particular algorithm later. Then by making sure that the two programs produce produce identical observable events, we can essentially establish correct translation, right? So in this case, both alloc and allocus instructions are observing the size and the allocated address contents of the new region. So if both are identical, then we'll be able to say that the two programs are behaving identically. So that's the higher level idea how we are proceeding here. So for example, if you consider the C program with the new semantics where we are producing observable events for the location as well. The new trace looks like this. So the part with yellow background is the new part where we are observing the allocations as well. So alloc begin says that we are performing an allocation for a local which is declared at allocation site I1. So the PC is I1, and it says that it is performing an allocation of 4 bytes, and these 4 bytes are these addresses. So hex 2002, hex 2003. Then it is saying that it has some initial memory contents and subx, and then it says that it was done with the allocation and then started with the call. And as you can see, the address passed to scanf is identical to the first address of the allocation of the allocated x, right? And similarly, you can see that the dealloc is happening after the scanf, so it corresponds to the instruction I4 here. So with this the new semantics of A, which you call annotated A, refinement is modeled as a as an existence of an annotation property. So we say that A defines C if there exists an annotation of A such that the behaviors of both are related by the refinement relation we defined earlier. So it's a C supersets A dot. Right? So recall that the relation we had said that uh, the in the program A, if it exhibits a trace T sub P, then either the trace corresponds to a stack overflow or to UB by C program, or the two traces are identical. So this assembly program would be producing identical trace as this one if the stack does not overflow and the C program does not perform. So what is the example? So this is I'm showing an example of annotated readint here. So just after the stack allocation by the stack pointer decrement 20 bytes, we are saying that the address ESP plus 16, so the last 4 bytes of the 20 allocated bytes, they correspond to the local X, right? And later we can see that the assembly program is computing this address ESP plus 16 in EX and then pushing it as the second argument to scanf, right? And in the scanf, call to scanf, we are annotating the arguments to scanf as well. So because CS scanf is a variable function, we are saying that it is accepting two arguments. So these two arguments are the memory 4 bytes at ESP and 4 bytes at ESP plus 4. So that's ESP, these two pushed arguments. And we are further saying that the scanf may potentially modify the heap and I1 as well. So the way these these annotations are made, we'll discuss later. But essentially, it is saying that the scanf procedure may only modify these parts of the assembly procedure and nothing else. For example, it is essentially saying that the scanf will preserve the caller stack of scanf, which means the read call stack of the stack contents of readint will remain identical, remain preserved. So this is one of the broad property we require for calling conventions, right? And at the end, there is DL of S, which is saying that the local X is being deallocated. So let's first go over the capabilities that this refinement definition supports. So one of the important properties that it supports merging of multiple allocations into a single stack pointer decrement. So for example, if the C program is allocating these three variables x, y, z, and the compiler has decided to perform a single stack pointer decrement for all of them, then we can support it by adding these three alloc annotations for each of them, right? So 20 out of the 20 bytes will have 12 bytes for these three locals. Similarly, a second important capability it has is support for dynamic allocations. So dynamic allocations are allocations that happen multiple times during the that may happen potentially occur multiple times during execution of a single execution of a procedure. For example, C supports these so-called variable length arrays, right? So you can have an array whose size is argument is variable. So for example, if I is one, then an array of size a single element will be allocated. But if I is two or three or up to n, then an array of n elements will be allocated. So in this case, the allocation size is varying per the iteration by the iteration variable of the loop. Right? So the way we support is that the annotation instruction appears inside the loop body. So for this allocation allocation in the unoptimized IR, an alloc instruction will be present, and corresponding to which we have an allocas instruction. So we'll be able to put both of them in a lockstep manner. So alloc will happen, then dealloc will happen, and if the next iteration of the loop executes, then both alloc and dealloc will happen. So both are still in lockstep. So we are able to correlate the both allocation deallocations on both sides. So notably, this capability of supporting dynamic allocations is missing in the verified compiler's COMSERT, which only supports pre-allocation. So COMSERT is a verified compiler which gives formal guarantees on the binaries it generates. So this is similar to a translation validation problem, but it approaches it in different manners. Instead of validating the single output of a compiler, it produces the COMSERT is a verified compiler, so it only produces verified uh, assembly, which is guaranteed to behave identical to the input C source, right? Now, a limitation of our current refinement relation is that we are producing these observable events. So if the observable events in both programs are not identical, recall that our trace is an ordered is an ordered attribute. So the orders are the order of the events are different, and traces will not be identical. So so for a refinement definition requires the order of observable events to be identical as well. So we essentially require that the allocation, deallocation, and the procedure calls happen in identical order across C to A. So one of the transformation where this ordering is not preserved is the are transformations that reuse stack space. So these transformations are I would say relatively rare. So, so practically it's not a big issue. So far we have only concerned ourselves with the semantics and definition of correctness. So what we want to produce is a method which help us automatically establish refinement. For example, we have not given a method how to annotate the assembly program. It's still we are assuming that it comes from an oracle. Right? So a method for establishing or witnessing refinement is a determinized product graph. So the product graph is a cross product of the control flow graphs of the CN, as annotated assembly A. So I just call CNA rather than dot A or anything. Uh, so a product graph essentially encodes a lockstep execution of CNA. So you have these two procedures which are executing instructions one by one. So product graph says that this path in C is correlated with this path in A, so that a single execution of the product graph edge corresponds to lockstep execution of these paths, right? And by forcing that the product graph edge corresponds to an acyclic computation, a bounded computation, we are able to achieve lockstep execution in the behaviors as well. So both programs will eventually catch up, essentially. So in the prior work, this lockstep correlation was of paths, and in our work, we are extending it to have a correlation of the deallocation, allocation, and procedure call events as well. So what we are doing is an lockstep correlation of paths and allocation, deallocation, and procedure call events. right? So a product program is a tuple of nodes. These corresponds to program points, where that is a program point in the assembly program and a C program. Edges, which correspond to acyclic paths in C and a deterministic choice map. A deterministic choice map determinizes the non-determinism in C to A. So essentially, this is the choice that the compiler makes. So we are essentially capturing that here. So for example, if there is an allocation in A, so we are saying that chooses a non-deterministic address in C and correlates it with a stack address in A. So we are saying that these two, the non-deterministic address in C is determinized to a particular stack address in A. So this deterministic choice map is determining the behavior of C based on A. And final elements of our tuple is a set of node invariants. So the product graph has invariants at each node, which help us in proving obligations related to correct translation. We call that our requirement is that the events must be identical, and the observable parts include the arguments of procedure call instructions and their values. So we need to prove those things. So for that we have node invariants which help us in discharging those obligations. Right. So the way so the way a deterministic determinized product graph witnesses a refinement relation that is considered a determinized product graph X. It will be said to refine a translation from C to A if it satisfies these 11 soundness requirements. So these 11 soundness requirements are categorized into two parts. So first we have these 7 structural requirements, and then we have 4 semantic requirements. So I'll go over each requirement. So first requirement is mutex A. So it is saying that the outgoing edges of the product graph have mutually exclusive paths. So it is essentially saying that at a program point in the product graph, you must have A for which all paths are mutually exclusive. So the behavior of the product graph is deterministic, at least on E front. And then in the second requirement, we say that we have the property called mutex C, the requirement called mutex C, which says that the set of paths correlated with a single A are mutually exclusive. So if you consider the total an edge outgoing from a node in X, its edge condition will be deterministic. So we have deterministic behavior of the product graph. Similarly, other properties are that termination, which is an exit node is correlated with an exit node. Single IO, which says that you must correlate observable events producing instructions in a separate manner. So single IO. So essentially, through this requirement, we are enforcing lockstep correlation of event producing instructions. Recall that our event producing instructions are allocation, deallocation, procedure call, and procedure return. So the next requirement is well-formedness. So it says that the determinized C program that we have, recall that we determinize C through our deterministic choice map. So determinized C program falsifies, that is part of X, falsifies well-formedness constraints only if A goes out of memory. So recall that if A goes out of memory, the refinement relation holds trivially. So we say that if A is not going out of memory, then C must satisfy the well-formedness constraint so that it remains well-formed throughout. Similarly, another edge case that we must handle is that the program A must exhibit UB. So A can also exhibit UB. So an undefined behavior in A would be accessing a memory that is not allocated. So say that say A is safe, such that A exhibits UB only if C exhibits UB. So if you have an incorrect program which is accessing out of bounds memory, then compiler is free to emit an assembly where the assembly is also exhibiting our out of bounds memory. So contrapositively, the if the C program was safe, then E must also be safe. So the next requirement we have on the structure is that the 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 two programs must behave at similar speed. So you must not have a empty cycle for C or A in an X loop. So essentially what you want is that both programs, if there are loops in both programs, then both programs essentially iterate the loops uh, 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 within a finite number of steps of each other. So, for example, if the C program is executing 7 steps, then the A program is allowed to exhibit 7x steps. But where x is a bounded, so you cannot. So essentially, to this we are essentially saying that you cannot have uh, have translations which convert or collapse a loop. Though not that this requirement is too constrained, it is excluding certain transformations. For example, you can have a closed loop computation for certain cases, so we are considering those out of scope for now. So the next requirements are our semantic requirements, and these correspond to queries or to publications over the product program X. So one of the first semantic requirement is coverage X, which says that X must contain all feasible executions of A. So essentially, what you are saying is that if A can behave in a certain manner, then X must be able to behave identically. Mod the case of a Stack Overflow, but we have already excluded that as we said earlier. Then the second is the coverage C. It says that if a set of paths are correlated with if a set of paths of C are correlated with the path in A, then at least one of them must execute to completion. So which is essentially saying that the execution of a product graph edge must happen. At least one of the edge must execute. So it's a non-blocking requirement. The product program must not get stuck somewhere, right? And the next is the inductiveness. So the node invariants that are referred, recall that our product graph X has a associated node invariants. So we are saying that there are particular node invariants and they are inductively provable. They are inductive node invariants. And then lastly, we are saying that the observables that have been produced so far are identical across C and A. So at a product graph node, the observables produced so far are identical. So you can already see that if you are able to prove that the observables produced so far are identical at every node, and you are able to correlate exits, then you'll be able to prove that the observable produced and the exit of the two programs are identical, thereby establishing correct refinement, right? And beyond these 11 requirements, we have two additional requirements that enable that are useful for a faster assembly encoding and other algorithmic optimizations. So these requirements are the first of them is the memory access correspondence, or MAC as we call it. So MAC is essentially saying that a non-stack or non-global region memory access in A is matched with an identical memory access in A C. So this point is a bit technical, so I'll just skip that. But the gist is that we are essentially saying that a heap access in A is matched in a heap access in C, right? So that these accesses happen in identical manner, right? And the second requirement that we have is that the memory states of the allocated regions, so the regions that are allocated at a particular node of the product graph, they are identical. So these two requirements are not strictly required for observing correct translation, but they help with the algorithmic optimizations. Right. And so what we have so far is a definition and a proof method, construction method. I'm sorry, not a construction method, but a witness method for witness for witnessing the correct translation. So what we need now is an automation, is an automatic method for constructing these determinized product graphs. So the way we approach is that we model it as a search problem. So we say that we'll search for a product graph X that satisfies these 11 soundness requirements. 11 plus 2 requirements, that the two are additional optimization related. And while we are searching for the product graph, we'll also search for the annotations of A that are required for observing correct translation. So essentially, what we have is a search problem where we construct the so it's a constructive approach where we construct the required product graph and annotated A incrementally. So this incremental construction essentially at each step we are essentially adding a particular behavior of A and identifying annotations as we go along, right? And while we are doing this construction, we use counter examples that are produced during proof applications or invariant inference for guiding the search. So this part is covered in the prior work. I want to explain this part. Uh, related to the identification of annotations, we have two methods for identifying annotations. So first is the black box approach, where we guess the required annotations. So we essentially through a restricted elimination, we produce a set of guesses, and because this is a search problem, we explore each guess one by one. So essentially, if the guess is incorrect, it's fine. We can reject it. Or if the guess is correct, we can proceed ahead, right? And the second method is a white box method where we can use untrusted hints. The point I want to emphasize here is that this white box approach relies on untrusted hints. These hints are not trusted, so they are still verified later on as part of the algorithm. So you can use these untrusted hints for guiding the annotation. So the sources of these white box hints are instrumented compilers. So you can essentially instrument the compiler to emit the point where allocation has happened, or the address which corresponds the stack address which corresponds to allocation. And then another source is debug headers that are produced when you pass certain compiler flags, for example, for GCC clients -G. Then you can obviously pass them manually as well. So for each allocation, you just say that these are the addresses that you want to go, right? So in our algorithm, the invariant inference, the technique that we use for identifying our node invariants is based on a guess and check procedure. So this guess and check procedure is guided by counter examples. So guess and check procedure has a set of candidate invariant sketches or templates, and through counter examples, it tries to reject certain shapes, and the shapes that are remaining, it tries to prove them. If it is falsified, then you get a counter example falsifying that, and you can reject that. So essentially, it's a iterative method using which you can identify inductive invariants. So the shapes that we have are affine shapes. For example, we have uh, sigma ori, ci into vi equals to c. So it's an affine shape. Then you have inequality, so that the variable is less than in this particular in EQC, the variable is less than a certain power of c. Then inequality where the operator where the relation is between two variables, and certain shapes particular to our well-formedness constraints. So you can they are discussed in paper. And last step is SMT encoding. So we have so far is is a method for correlating for identifying notations. We have the node invariant. So what we want to do is we want to discharge a proof obligation to the SMT solver. So the way the way you encode the proof obligation matters a lot in these cases. So in our case, our SMT encoding uh, is a predicate represented as a first order in first order logic, where the language is based on bit vectors, arrays, and uninterpreted functions. So one particular obligation that we do is an allocation state relation, which says that an address alpha belongs to region R. So you can see that this particular sorry, you can see that this particular relation is required for example, for proving well-formedness of a of a stack allocation. So recall that the constraint requires that the address range that you're trying to allocate to belong to stack. So the proof obligation would be discharged for that performance check. So what we have is we have three different encodings for this operation. So first is the full array encoding, which is a naive encoding, which uses arrays for encoding this particular relation. Second is partial array encoding, which is an improvement over full array encoding, and it is able to encode certain address set relations using bit vector comparisons, which are faster for the assembly solver to discharge. And then we have a full interval encoding, which is an optimized encoding, and it is only possible if certain program shape is available. For example, it cannot be used if aloca is present in a loop, right? So aloca is kind of a niche construct that is not even in the C standard. So essentially, you can always do full interval encoding for most practical programs. And full interval encoding does not use arrays, so it is usually very faster to discharge than the two encodings. So experiments. So
Hey,
our system
Abhishek,
is yes,
yes, sorry, we are actually running out of time. So would it be possible to wrap up in a minute or two?
sure.
Yeah, yeah, thanks.
Yeah, so in our experiment, we are essentially validating these three capabilities. So you want to validate our capability to handle diverse local patterns. You want to compare and evaluate the performance cost of our encodings, and you want to quantify the cost of performing annotations, and we want to test our system on a real world program, right? So programming patterns as part of the first evaluation involves almost all the construct that the C language supports. And of these benchmarks, we have a success rate of 83% essentially. So we are able to, we have quite good, I would say, success rate for case of compilations where the compilations are performed by industrial strength compilers at O3 optimization level, right? And a second benchmark was that was is about identifying cost of annotations, and in that the gist is that we find that the annotation imposes identifying annotation imposes a significant cost over in the runtime of the program. So essentially, we find that on average, if you do not have to identify cost, then you run 2.5 times faster. And in our third experiment, we run our system on a real world benchmark where we find out that we have a success rate of 88% if you use a lower optimization level. And I guess that's it. So essentially, I'll go over the contributions once again. So our first contribution is our set of formats execution semantics for the correct translation task, and then we have refinement relation for the same task, and an algorithm for identifying the correct product program for correct translation, and we have prototype implementation and evaluation. So thank you.
So, thanks, Abhishek. Unfortunately, we are running out of time and I have a meeting in a minute.
Okay,
So, I don't think we'll be able to take questions now, but, if audience have questions, they may email you. and they can contact you directly, right? So,
Okay.
yeah, I think I need to stop now. So thanks again. Thanks for the detailed talk. Even I have few questions, but I don't have time to ask questions now. All right. Uh,
Okay.
yeah. So
Okay.
let me just stop the recording.